Okay, we're good on. Check, check. There we go. Welcome. If you came to learn how to hack Metasploit, this is the wrong class. We are talking about software-defined radio. Excellent. And I think this is the fullest room, this is my 5th year presenting at SAINTCON. I think this is my fullest room I've ever had, so go Clown World. I'm glad you're all here. Thanks for coming. Can we give John and Ben a round of applause for running this whole thing back here? They're killing it. They're doing great. Awesome. Well, thanks for coming. We're going to talk about some RF. We're probably a little more on the 101 side than we are on the advanced side, but I'll field questions and answer as much stuff as I can. So does anybody know what this is? The Russian woodpecker, that's absolutely right. And I heard somebody over here say Duga, I think, as well. So this is the over-the-horizon radar that the Soviets came up with to try to determine early missile launches from the West back during the Cold War. And when they turned it on, it blew out all frequencies in kind of the shortwave area. So I mean, this thing's large. You can see that building kind of down in the foreground there. That's like a 5-story building. And then you can compare that. Those trees are like full-on trees. Like this is a pretty recent photo. I would say late 90s probably. And I mean, the Soviet Union hasn't really manicured their area in a long time. So those trees are full-height trees. And then you see how tall that thing is. This is about, and sorry, I'm like obsessed with this thing. So you're getting a little more than you wanted. But this is about 1 kilometer from Chernobyl. Has anybody heard of Chernobyl? Yeah, not great. The show's great, though. Watch that if you haven't. They were worried about this rusting and falling and causing microquakes that would break the concrete encasement that was previously over Reactor 3 at Chernobyl, the one that melted down. Now they're building a whole metal structure over top of it. It's a little bit more secure now, but this thing is large. Anyway, it might be the biggest radio antenna in the history of the world. I'm guessing it is. Anyone want to prove that wrong? Let me know. It's big. And it's got its little brother over there. I think that was the predecessor. And it needed so much power, it was built close to Chernobyl, which was the power plant. So it broadcast about 10 megawatts, which, if you're familiar, your little handheld ham radio walkie-talkie is anywhere from like 2 to 5. 6 or 7 if you're like breaking the rules, but that's watts, right? That's 5 or 6 watts. This is 10 megawatts. It was giant. Anyway, so this thing's cool. It's not in production anymore. It's been decommissioned, but super cool. A lot of steel there. Anyway, so my name's Erich Ficker. I work at a place called Moss Adams. Mainly an accounting firm. We do some IT audit. I run the pen testing practice there. I like cycling, hacking. I like cars. I went to UVSC before it was a new UVU. Master's at University of London. If anybody's BYU students, yeah, don't be ashamed. I teach adjunct there, and this winter I'm teaching a class called Cyber Risk Assessment, which is really just hacking. I just had to give it a nice name so the admin would let it flow through. Some certs, there's my contact info. Anyway, let's get going. Okay, so the electromagnetic spectrum is basically just, it includes light. It includes this whole range. If you can see from the very end there, it starts at 0 and goes all the way to past light, basically. It's measured in hertz. A hertz is something that happens, 1 hertz is once per second. So frequencies are measured in how many times the wave oscillates. Okay, electromagnetic waves, they're just waves, nothing too special. So how many times that moves in a second is the frequency. So Wi-Fi is 2.4 or 5 gigahertz. That's pretty fast, and it's a small wave. We're going to talk more about that. It's a broadcast medium. What does that mean? You can't just send it to, I can't just send it to you. I can send this to you. I can't send a message from myself to yourself because all of you will also get it. because it bleeds out. It's a broadcast, right? I have to protect that communication if I want it to just go to you and have you just receive it. So it's a broadcast medium. It goes out. It's kind of the Wild West, right? It goes out everywhere. Just kind of spray it all over the place. It moves the speed of light, which is pretty fast. Does anybody know what the speed of light is in miles per hour? Miles per second, that's right, you're both right. 186,000 miles per second, so that's pretty speedy, right? We can modify it so we can carry data. Obviously, everybody uses Wi-Fi, Bluetooth, all those things are on RF. Carry data. This is a big old convoluted diagram, not in English, because I thought it made it more confusing because it wasn't in English, of kind of the electromagnetic spectrum. We're not going to spend any time on that. This is even more convoluted, and this is the United States FCC band plan, which means what they said, these frequency bands or areas are going to be used for these specific things. That's even more convoluted. So this doesn't have anything to do with receiving, because you can receive anytime on anything. You're not causing any trouble. When you're going to broadcast, you have to basically check, okay, what am I broadcasting on? Is it interfering with anybody? Or the FCC might get grumpy with you, okay? We covered some of this already. Broadcast to as many recipients as can in range. For a long time, they didn't know where the Russian woodpecker was, because it would come on in bursts and then it would turn off. So they would have to catch it and kind of triangulate it. Eventually they figured it out. NATO actually knew this was built, but apparently it was top secret. So anyway, eventually they figured out it was in Russia, got nicknamed the Russian woodpecker. But even that's a giant signal, 10 megawatts, blowing out all kinds of shortwave across, basically across most of the planet. And they still had took a minute to figure it out where it was coming from. The other thing is it's impossible to determine who is receiving this signal, because it's a broadcast. If you guys, before like cord cutting for cable, right? Nielsen Media Research would install little TV tuners inside people's TVs to figure out what they're watching so they could get ratings and report those ratings back to networks and advertisers, that kind of thing. That's how hard it is to figure out who's getting it. They actually have to put something in the TV to figure out what they're, now that we're on Netflix and Amazon, they have, I'm sure, awesome data, who's watching what. They know what you were watching. I don't know if you want your mom finding out about that, but that's fine. So layer one, it's just pulses on a wave, right? We're just changing how the wave is shaped, how far it moves, and then we're going to interpret that as data. We put it on as data, it comes off as data. So just like Cat5, you've got electrical pulses. These are just a wave. It's a little bit slower than a wire because it's over the air, right? Still at the speed of light, which is similar to Cat5. Actually, it's just short of the speed of light, but you have to catch so many waves to get the data, where on a direct connection or a wire, you've got the exact pulses, right? 0 or 1. Okay. Maybe. Oop, there we go. Okay, so obviously RF use in the wild. We've got on Wi-Fi, Bluetooth. Everybody uses those, right? FM radio, satellites, your cell phone, at your house. So this is my power meter. It is bolted to my house. What happens if, so it's RF, they come and drive a truck around, and I believe this creates some sort of a mesh network with my neighbors and then reports back in chunks to the trucks. So if that develops some sort of a vulnerability where somebody could read or modify my data, would that have any kind of impact? Yeah, and it's pretty sticky, right? Like that thing's, I don't know how much those cost. I think they replaced those when they put those in for free. Any of the Provo residents, I'm sure they just swapped those out for us so they could collect them easier, collect the data easier. But I assume $300 or $400, right, for just the parts. And then I don't really see those guys walking up and doing software firmware updates to my power meter. So when was the last time Eaton and Itron got together and had a pen test on their RF data encryption? I don't know. And maybe nobody cares. I don't know. I care, but this is bolted to my water main, so same deal. They measure my water usage by driving a truck around, a little antenna on top of the cover that covers this up. But again, pretty sticky. This doesn't actuate any water main or anything like that, so there's no kind of physical attack, but still data there, data we can grab. There are, we'll talk about it a little bit more in a minute, but I mean, there are meters that have broken encoding, not broken, I guess. People have broken the encoding to grab that data. So it could be interesting. Could be interesting to, the one library I read about on these was the guy said he wanted to troubleshoot a leak in his house, so he wanted to gather the data for himself, so then he could determine where the leak was coming from. But you can guess. I mean, if this is a mesh network with my neighbors, right? I could say, oh, I'm interested in this neighbor, and this is the ID of his water meter, her water meter. Now, when I see no water being used for maybe a day or two, I know my neighbor is no longer home. So then what could I do? Maybe I like my neighbor's stuff, and I want to go get my neighbor's stuff, and I know they're not home. So anyway, some interesting attacks, I think, could be inferred from gathering data from things that are attached to your house that you basically have no control over, right? You can't call Provo and say, hey, I don't want the Neptune meter anymore. I want the Saturn meter because it has better encryption. They're going to laugh, right? We don't know what you're talking about. Also, get off our phone. So, yeah, and this stuff is just, again, broadcast. So if you can grab that data, then there's lots of stuff like this, which is kind of fun. Your car, most of your cars probably, if they're, I don't know what the year is, they started requiring these, but everybody know what a TPMS sensor is, tire pressure monitoring system. Every one of your tires has an RF transmitter in it that tells your car what your air pressure is in your tire. So and they all have a unique ID. So if you wanted to track who was coming into or leaving a neighborhood, I don't know, maybe you'd put a box somewhere inconspicuous with the antenna and see if you could grab those unique IDs from your neighbor's cars and then track their movements. You're not touching their car. Is it against the law? I don't know. It's broadcasting everywhere. Interesting. There's interesting stuff with RF that's kind of like gone away from the other side of things, from like, I mean, there's still vulns in web apps, there's still vulns in firewalls, sort of. There's still, network vulns, system vulns, those all still exist, but they're usually these days are a little bit better patched, a little bit better tracked. Unless you've got a pretty negligent organization, they're getting pen tests, they're getting audits, but this kind of stuff just goes out into everywhere, right? So it's interesting. Aircraft transponders, since 2020, the FAA has required every plane to have an ADBS transmitter on your plane. So that's small planes, big planes, all planes. If you're in the air, you have to have one of these transmitters. And it gives you position and elevation and your call sign. So there's one that I picked up. We'll talk a little more about that as well. But so those could be interesting. Of course, you could just go on FlightAware, right, and just look at it anyway. That data apparently is public. Is that a good thing? I don't know. I don't think they could keep it from not being public. But so yeah, interesting. So this is Orem's water system. Why is this interesting? Well, one, it's interesting that this is a critical infrastructure, and it took me about 30 seconds on Google to find a map of every main line pipe in Orem. I also know where their tanks are. You can see the tanks on there in cyan. And then a couple of treatment. All those little black triangles are water pressure releases. The tanks are interesting because wherever they take water and introduce it into the system, they have to add what? What do they add to the water? Chlorine, right, because they're trying to kill bacteria, make the water safe for us to drink. Chlorine in concentrated amounts is good or bad? It's bad. Bad enough to where if one of these stations has a leak, they have to empty, I don't know what the radius is, but neighborhoods. Like you're evacuating neighborhoods. if you have a chlorine gas leak at one of these places. It doesn't happen very often, which I'm actually pretty surprised about. I'm hoping it's because they have good safety measures in place and they're audited a lot, and they just take care of it, but let's hope, right? I actually haven't heard of it. Has anybody heard of chlorine gas leak from a water treatment system in a city? So PG Pool had a leak, and they're probably not even dealing with the same amount of chlorine as like water treatment, right? And that's still a bad deal. Somebody raise their hand back there. Okay, another pool deal. That's a lot. That's a lot, and that's just a pool, right? That's just a couple 100,000 gallons of water. We're talking about, on these systems, that's an hour probably. So a lot more chlorine, a lot more concentrated, and those little outbuildings are kind of all over the place. Now, the reason I bring all of this up is because on all of those outbuildings, there is an antenna. We'll talk about that in a minute. So, okay. So what is SDR? All it is it's just a way for computers to talk to RF, okay? So uses integrated circuits to control the radio, to tune it to a specific frequency, and to listen on that frequency. That's basically all it is. Pretty straightforward. Usually has a decent range, controlled by software. GNU Radio. Has anybody used GNU Radio before? Oh, my advanced users, I like it. So GNU Radio is awesome because you can basically build a little radio in software, take the signal from your adapter, run it through this radio filters, and get the exact specific signal that you want to get a really clean signal. So GNU Radio is really cool, more on the advanced side. WinSDR is more of a software. We're going to talk about those in a second, so I'll skip that for now. Oops. And then, yeah, just needs a hardware adapter, so the radio can, so we can interface with RF. Okay, so tools of the trade. This is the hardware. Now, the coolest part about SDR, and I think when it really started to blow up, was because of the RTL SDR. Has anybody heard of the RTL SDR? Yep, lots of you. Awesome. So this thing's sweet. It started as a TV tuner, basically a TV tuner card, if you remember those from way back in the day, where you could tune into TV signals, receive them on your computer. Which back when like there were no DVDs or anything, which is basically when this was, or maybe about the same time, you could watch TV on your computer, which was kind of cool, and record it. And I think that was probably the start of like, I don't know, video sharing, that kind of thing. But they figured out that this chip was pretty versatile. And it wasn't locked down to the specific TV frequencies. So then, of course, this chip's already being made. It's pretty inexpensive, and you can buy these for about $40. So your total cost to enter an SDR, messing around, listening to stuff, is about $40. Maybe with an antenna, it's $42 or something. Those are two different ones there. One, I think, has, I can't remember the difference between the two, but they both basically do the same thing. That's their range of receiving frequency, which is pretty wide, right? Almost to Wi-Fi and all the way down to 25 megahertz, which is a really wide range. Then you can kind of pre-filter your signal with different adapters. These can either be powered by external power, battery, or USB, or through the adapter if that has the ability to do that. And those allow you to either shift where your adapter can receive frequencies, what frequencies it can receive, or it can hyper-focus on very specific frequencies to get you a really clean signal, or boost the signal altogether to get you, if it's a weaker signal, because when you're capturing data from the signal, you want it to be as clean as possible to avoid, garbage data. Basically, you want to get all the ones and all the zeros, and you don't want to get them mixed up. So those are probably $30 or $40 a piece as well. You can do that in software. Sometimes it's harder to do in software, so it's come in handy. This is called the AirSpy. The AirSpy is really cool. It has a similar range, if you notice, to the RTL SDR. The AirSpy is a lot higher quality. It's a different chip. These are about $130, I think. but produce really clean signals, just a higher quality of reception. Can it do things RTL SDR can't do? Debatable. It is a cleaner signal for sure, so depends on what your goals are. The SPYverter is kind of an add-on to the AirSpy, allows you to drop down way below that 24 megahertz floor on the AirSpy, down to 1 kilohertz, which is pretty slow. That's 1,000 oscillations a second, which for RF is very slow. Yeah, so stick your ear next to it. The beauty of the SPYverter is you get down into kind of the shortwave frequencies, which are kind of start at around 25 megahertz and go down. So it allows you to kind of get into that area. And shortwave is really cool because it can travel really far. And you can pick up signals from basically all over the earth, depending on the weather, right, or the time of day. Affects RF as well. So those are really cool. Again, those are all receivers. All of those things we talked about are receivers. And then this guy, the yardstick one on your right, is probably my favorite SDR tool. I think they're $100. Michael Osman created them, but the chip that it uses is from an IM-Me, which is a toy. If anybody's ever heard of the IM-Me, raise your hand. Yeah, because they're cool. You do cool stuff with them, right? So it's just this little children's toy that you could like send messages to somebody that was line of sight. So it's just a little radio transceiver, basically. But they took the chip out and they're like, hey, we can do cool things with this thing. I think now I'm going to forget his name. They repurposed it to open garage doors. Who did that? Yep, Sammy Kankar, that's right. So anyway, lots of cool stuff you can do with this little device that was a kid's toy, right? So he took the chip, put it on this device, and now we can put different firmware on it and control it with my favorite language, Python. So you can send signals using Python, which is cool. You can also receive signals. If you have the right library, you can decipher those into data and do all kinds of cool experimental things. The device to the left that I didn't even list is called a crazy radio. Has anybody heard of a crazy radio before? This guy, he's heard of them all. Oh, you've heard of them all, haven't you? I like it. Okay, so the crazy radio is cool. Has anyone heard of the HID RF attack, where you can attack keyboards, this thing, and if anybody has one right now and you want to, I give you full license to go for it. But basically, keyboards usually have some sort of authentication to their dongles or their adapters. This is more of a mouse with some buttons. And mice, this and mice don't at all. So you can grab signals that these make, including the equivalent of a MAC address, and then attack it using that little adapter. I think they're $10. Maybe $20 if you want to wait for shipping. BetterCap, there's a section of tools called HID and BetterCap. Has anybody used BetterCap in here? Oh, you should all use BetterCap. It's super freaking sweet. So you can use BetterCap to do HID attacks on these, which is cool. That's step one. Grab one of these and go screw around with BetterCap. It's cool. And then this is the grandmaster of all RF, SDR, the Hack RF1. So there are other ones. Blade RF, I think, is another one. There's some higher end ones. This one's about, for the legit one that, again, Michael Osman makes this. I think they're about $300. This one has the PortaPack, which allows you to run a little bit different firmware and actually use the Hack RF1 without a computer completely. It's got a screen on there, little input wheel and arrows and button and stuff, so you can do things that without a computer completely. The one on the bottom's a knockoff, but he released all his stuff open hardware, so I don't think he's super worried about it. I have both. I've used both. The Hack RF, I think it's a little bit cleaner signal, which you'd expect, but the knockoff does about all the things. And Hack RF, I think the Portapack's I want to say it's $130, something like that. So that plus the Hack RF and an enclosure approaching $500. The knockoff's about $200, so $220 maybe. So a little bit more affordable. Does mostly the same stuff. So if you want to get into transmitting, which is where things kind of really get fun, Yardstick one, Crazy Radio, the Hack RF ones are kind of where you want to go. But again, you can start for $40 with an RTL SDR and just start messing around. Okay, so software. So Dragon OS, Ubuntu-based distribution with tools installed. It's okay, works. It's got some stuff on there. You could also go out and grab the tools, compile them yourself, and on a normal Ubuntu. So this just short circuits a couple of steps if you're lazy like me, which I enjoyed. So, and then PySDR is kind of similar thing, but runs on a Raspberry Pi that we all love, right? So, similar. I think this is a little bit better put together, to be honest, than Dragon. But the Pi is great for SDR because it's cheap. You've got Linux. And it doesn't matter what your other machine is, right? You can have a Linux machine talking to it. You can have a Windows machine talking to it. You can have a Mac, which I'm stuck with. So that's nice because we get access to a Linux machine that a lot of tools are built on. And then for kind of general discovery, I just covered an example for each OS. So as much as I hate to admit it, the SDR Sharp on Windows, which is actually made by the people that make the AirSpy receiver, is probably the best one. Now, hacking tools on Windows makes me sad inside a little bit. Apologies for any Windows fans, but it's the best one. It's got lots of stuff that makes it a little bit easier to identify where you are in the spectrum, identify signals. The waterfall is pretty descriptive as well. You can see kind of those stripes in the middle. That's the waterfall. Shows you kind of how the signals are progressing over time. And then at the top, you can kind of see where each one of those peaks is a signal, and it's doing something, right? We don't know what, but there's something being broadcast there. So SDR Sharp's pretty good on Windows. And then if you're on Mac, Cubic SDR is a little bit more bare bones, but does get the job done. I did a lot of discovery with that preparation for this, and it's good. Not quite as many features, but it's in the App Store. It's easy to install, right? So no hoops to jump through. And then on Linux, there's SDR Plus, which is open source, which is cool. A little bit more featured than Cubic. Not quite as developed as SDR Sharp, but basically for any platform, you have a GUI tool that you can pop in there, plug in your $40 RTL SDR, and start exploring the RF spectrum, which I think is pretty rad. Before the RTL SDR, it was hundreds of dollars to get some sort of device to get your computer to talk to RF, right? It predates the Hack RF, so that didn't exist at the time. It was kind of a specialty area. That kind of opened it up to all of us, nice people that don't want to spend a couple $1,000 on an SDR adapter. And then as far as software goes, this is where things start to get interesting. So you can do a bunch of exploration using these tools, using the hardware, but there's lots of libraries and lots of tools that are very specific to a very specific thing. I mentioned the power meter on my house earlier. There's a specific library that you can grab off GitHub and start grabbing data from that, from your water meter. So I didn't write any of those, but I'm sure as heck fire are going to use them all because they're right there and I can do cool stuff with them. So that's where things start to kind of get interesting. Although I don't want to downplay just the general exploration, because I sat probably in my living room with Cubic and a RTL SDR for, I don't know, 3 or 4 hours just exploring the range that it could receive on. All kinds of interesting stuff I couldn't decipher. You can cover FM in there. I don't know why, but like I don't listen to the radio ever because it's the radio. But I'm just this young enough to not be a boomer. But for some reason, getting an FM radio broadcast on my computer was super cool. I don't know why, but it is. So anyway, okay, so we've covered hardware, we've covered software. Now let's look at probably the most important part of, well, they're all important, but one of the more important parts of this is the antenna. So these are different. We're going to cover the different types, and we're going to cover when you want to use specific antennas. Okay, so monopole, it's just an antenna. Just goes like this. You can see that giant tower. The antenna is that little tiny white thing at the very top. The tower is just to give it elevation, to get it out of any kind of obstructions that are around it, so it can get line of sight to lots of places. It's just basically a wire, usually vertical, and it emits whatever's transmitting on it emits the RF through that wire. We'll talk about wavelengths and how big antennas should be in just a moment, but the shape of a monopole or omnidirectional antenna is like a donut. So it's a big donut, starts at the middle, that's where the signal comes out, and from there it just waves out in kind of a circle, right? It's hard to describe in 2D space, but it's a donut. So that's how it goes. It goes out in every direction in equal strengths, okay? Covers a lot of area in a circle, not the greatest for long-range communication, unless you got a giant mast like this. Okay, dipole. This is a Yagi. Has anybody heard of a Yagi? Yagis are cool, right? So directional antenna, great for longer distances, but it broadcasts in a cone, okay? So if you want to talk to another antenna that's 10 miles away, your omnidirectional may not make that happen unless you give it a bunch of power and then the FCC gets grumpy at you. So on a Yagi, though, you can beam it straight, you can point them right at each other, and for relatively low power, talk for a pretty long distance. The other thing a Yagi gives you is some privacy, right? Now that you've got a cone, or it's a little more cylindrical, but it bleeds off for sure. So, but if you're behind it or to the side of it, it's probably harder to pick up that signal, especially at any kind of distance. If you're close, you can probably still get it, but anyway. Aperture, so this is just a dish antenna. The signal concentrates in the dish and then puts it out to the element, which is out on the middle there, and great for long distances, directed transmissions. A loop antenna, it's kind of funky. I don't know that much about a loop antenna, to be honest with you. I did use one when I played with shortwave a little bit, but I think it's better for lower frequencies. So array, lots of antennas working together. Okay, the Duga was one of these. Every one of those vertical kind of sets of towers has, 10 or 15 elements that are broadcasting. So those are all working together. And then you also want the antenna sized to match your wavelength. Your wavelength is determined by your frequency. So that's a little bit more on that in a moment. So the antenna is a very important part of the system. It's probably the dumbest part of the system. It doesn't really do anything other than broadcast the signal, right? Power goes to it, it goes out. There's no moving pieces, there's nothing really happening there. But if it's sized wrong or if it's the wrong antenna, you're going to have a hard time getting the signal or achieving your goal of doing whatever it is you want to do. Okay, so different types of RF attacks. So eavesdropping is the most obvious, right? It costs you $40 to get into. You can grab signals from whatever's being broadcast within your range. Okay, pretty easy. That may be sensitive data, it may not be sensitive data. Maybe how much pressure's in your car tire, that also tells me that you're leaving the neighborhood. It may be how much water you're using, it tells me you're home. It may tell me how much power you're using. I don't know. Man in the middle attacks, These are a little bit harder to achieve than if you had like a Wi-Fi man in the middle. Historically, you'd think of like you're connected to a rogue access point. That access point has a bad actor. Then they're forwarding on data, and you're interrupting that communication. This would be more of you're grabbing broadcast data, rebroadcasting it, and saying, hey, I'm the legitimate one, not the other one you were talking to. So a little bit different on RF. And then replay, which is probably one of the lowest brow attacks ever, because all you have to do is record a signal and then play it back. So you're not doing anything to it. You don't have to decipher it. You don't have to grab the data out of it. Excuse me. So in 2016, I don't know if it's this room or that room, but I presented on some home automation, home security systems, and one of them was vulnerable to replay attacks from the keypad to the kind of main system. So yeah, if you're bored or can't sleep, look up Ficker, my last name, SAINTCON 2016, and all you had to do was capture the signal from the keypad of somebody unlocking their house, basically turning it off when they get home, and then record that, play it back whenever you want, and it would just do this. It would disable the system. So that was super lowbrow. It's basically the phone phreaking, like payphones. Anybody familiar? Like you play the tone and you get credit, right? So I mean, it's worse than that, right? Because instead of free phone calls, now you're disabling someone's home security system. So replay, while it is probably the easiest thing to do in the world, and all of the RTL SDR, so all the RTL SDR can receive that data and record that data. You'd need a transceiver or a hack RF1 or a yardstick to replay that data, but it's pretty cool. Most home automation systems are vulnerable to this on most devices. During that same research I did for that was actually part of my master's thesis, but most of the systems were vulnerable to that on most components. Deadbolts, thankfully, did have encryption on Z-Wave, so those could not be replayed, but I could turn lights on and off. I could pretend somebody's window opened or closed. More of an annoyance. Luckily, nobody could just hit it and walk into your front door, right? I could disable your alarm if you had the right alarm and, lockpick your door and come in and you wouldn't know, but and then forged message. So forged message is, I know how the system works, or I have a library that knows how the system works. I'm just going to create my own messages, do whatever I want. So that would be true for if I was able to break the encryption on a deadbolt, then I could forge a message, right? Because I knew the encryption, or if I was able to get the key, then that encryption key, then I could forge a message to say unlock, what have you. So forged message is probably the most interesting, although replay is probably the most fun because it takes no work. And if the system is vulnerable to it, just record lots of different things of what you want to do. Turn on the light in the living room, turn off the light in the living room, turn on the light in the bedroom, turn on the fan in the bedroom. So there's, anyway, all this stuff's super interesting to me. I hope you guys are interested in it as well. Any Formula One fans? Yes. Favorite team? Nice. All you need to know is Mercedes is evil. And I only like Red Bull because they have the ability to beat Mercedes. So, anyway, again, car nerd. So, here's how you start to access SDR now that we've covered kind of all the bases of what goes into it. Your frequency is going to determine the wavelength, okay? So frequency, if you recall, is in hertz, right? I'm going to go through a couple examples, so you don't have to memorize this on the first slide. But the wavelength will dictate your antenna, what you're using for your antenna, kind of sizing. and obviously what you tune to using the radio. Okay, so if you know your target's on 900 megahertz or 905 megahertz, and that's what you're going to tune your radio to, and you're going to get an antenna that matches that wavelength. Okay, and you can look that up. That's super easy. You can just say 900 megahertz wavelength in Google, and it'll tell you what the length is. I'll show you what to do with that in a minute. Okay. So this. Okay, let me see. This may be total technology fail. So you may say, well, I don't know what the frequency is because I'm looking at a device. It doesn't tell me what it is. So the FCC is really cool because when you make a device that emits RF, you have to submit it to them for approval, and they make all that data public. So this FCC I/O is just like a URL shortener that's actually super cool because all you have to do, if you remember that power meter I showed you a photo of on my house, all I did here was, and all you have to do for this URL is FCC I/O and then the FCC ID, which is printed on the face of that power meter. So I don't know what frequency that operates on. It doesn't say on the sticker. Let me see if I'm going to be able to. So I'm going to click this. Maybe. I might have to go. All right. I'll just copy it. How about that? Is it going to show you? Oh, yeah, sweet. Okay. So let me open this up a little bit. I'm just going to paste that URL right in there. So all that is FCC-IO, the FCC ID, which is printed on the face of that meter, and then it's going to take us right to the FCC website. And here is the entry for that. It's going to be a little hard to read. Let me see if I can make that a little bit bigger. So we'll go to, we don't want the summary, we want the detail, right? So let's, yeah, okay. And then in here we've got, external photos. That's interesting. So looks like 2013, so I'm sure that firmware is like totally up to date because that was only a few years ago. So we can look at, let's look at external photos. Let's see if this is really the device I have on my house. There's the board, looks generally like the right shape, okay? And then, let's see, did that open a new window? Yeah. So internal, that looks like an internal photo actually. Let's see what's an internal. So basically, that's the unit right there, right? So that could be interesting if you're really trying to attack it at kind of the physical layer. All of this stuff's public information. The other thing that's interesting that I skipped past on the first page is, this right here. So we know now that it operates between 902 and 927 megahertz. So in that range, all I need to do now is make sure I have an antenna the right size, tune my RTL SDR to, start at 902.0, go stand next to my power meter and just go across that spectrum, that 20 megahertz, 25 megahertz, and see when I have a big spike in broadcast. That's my frequency. Now I know where my power meter is broadcasting on. So that's super easy, like super easy. It's public data. FCC makes it even easier. And your FCC ID has to be printed on all of your devices that emit RF. So there's your key to figuring out what the frequency is. All right, back to business. All right, so the direction or the distance you want to go is going to determine your antenna. Okay, so if you know that you want to capture a wide range, then you want a monopole, right? You want an omnidirectional antenna. If you want to go a far distance, but you don't care as much about what's on the sidelines, you're targeting something specific, then you want a Yagi or something directional. I'm going to need to blast through these a little bit. Okay, so your goals are going to dictate what your SDR adapter is. If you're just trying to listen and receive, RTL SDR is fine. AirSpy is fine. If you want to broadcast, really mess with stuff, then you need a transceiver, hack RF1, yardstick 1. And then whatever your attack or research is going to determine what software you're using. If you're just doing discovery, one of those general tuner softwares will work. If you're going farther and doing something else, you may have to write your own library. Lots of stuff that's common has libraries written for it already. Search around. Okay, so here's a specific example. ADSB is the airplane transponders, okay? And this is I just pulled out the right tools, hooked it all up, and went for it. Okay, so frequency is 1090 megahertz, okay, or whatever that is in gigahertz, less than that, 1.09 gigahertz. So the wavelength for that, as I found from Googling it, is 275 millimeters. That's pretty long for an antenna, so I'm going to divide it by 4. You can use antennas in different waves, they call them. Okay, so this is going to be a quarter wave antenna because it's divided by 4. 69 millimeters, pretty easy, pretty short antenna. I had one laying around. You can buy like a box of antennas for like $20 on Amazon, so they're not expensive. Different lengths. You can also use a telescoping antenna. One comes with a hack RF one. Measure it, get it to the right length you need, and there's your wave. Okay. So I use 69 millimeters, a quarter wave antenna for the 1090 megahertz. And then I knew that planes are all around me, right? I don't know where they are. I'm not going to point at them. I just want to gather data from wherever they are, right? So Omni Direction was the right move. Monopole antenna, which sounds really cool, but it's just one of these, right? It's just straight up. And then I just wanted to listen and capture, so RTL SDR was perfect for that. And I should have not put a tag, I should have put a research, right? Research, I wanted to map where planes were, because I think that's cool. And they're telling me where they are, so why not throw them on a map? Okay, so this is the raw output of that, latitude, longitude, call signs, how many packets they've sent me, and then this is the map. And software dump is called dump 1090. This is all kind of part of it, right? So you just compile this, run it, and it puts on a map on a web server for you. You can pull it from anything on the same network. It's kind of hard to see the planes there, but there's a plane at the bottom, there's one in the middle, and there's one all the way up in Salt Lake that I was able to get from my backyard in Provo. Kind of cool. And that's my super high-tech setup. I use a coffee can as kind of the back plane for that thing, or a food can maybe, and $40 RTL SDR garbage antenna. Okay, the other thing you do, FlightAware does make a Pi-aware version, which is FlightAware that runs on a Raspberry Pi, our favorite Linux computer. So a little prettier, right? It's a little bit more of a closed system, but super easy to spin up. Throw it on an SD card, throw RTL SDR into the USB antenna, you're off and gathering data. It will share this to FlightAware if you tell it to, which is kind of cool. I kind of like dump 1090 better because it was just kind of like running locally and I didn't have to worry about any of this commercial stuff, but whatever. Or you can use HackRF1 with the backpack and the custom firmware that's called Mayhem, which actually has a lot more functionality than just this, but you can go to ADSB function on the, what is that? In the middle there, you can see the planes it's seen, it's a little dark, and then you click on one, it's touchscreen, click on one, click See on Map, your SD card, you load an SD card up with maps, and then there it is, right there in Provo. So that, you don't need a computer, it's a little box that can be battery powered. Okay, so this is another receiving exercise, pretty sweet, because we're now going to talk to a satellite. We're going to let it talk to us, I guess I should say. Frequency is 1700 megahertz, which is pretty close to what very widely used RF system? Yes, what else? More commonly used. It's close enough to Wi-Fi, okay? So Wi-Fi is 2.4, 1.7. It's pretty close enough that we can use a Wi-Fi directional antenna, and I'll show you that in just a second. We do want a dish antenna, directional, because we are talking to something that is 22,000 miles away, which I think is pretty cool. We're just going to listen capture. I'm going to use RTL SDR with a special filter that basically just enhances that specific signal called the Sawbird. I think it was $30 or something. And then we're just going to capture data, and this is what that data looks like. So there's my awesome setup, another Raspberry Pi. The filter you can see installed above between the antenna wire and the RTL SDR there. And then you have to kind of aim it because the thing's pretty far away. There's two of them you can tune to. Closest one is kind of on the way to Hawaii. And then there's my super cool Wi-Fi dish, and then running by itself, battery powered with the Pi. I just left it out there for half a day or so. and then you can download like super cool images of the Earth from a satellite. Like this is not, you could go on Google and just Google ghost satellite images. This is an image, when I downloaded, it was about 10 minutes old, of the weather systems on the planet currently. I think it's pretty sweet. And you don't need the interwebs. And then you can also look at, there's different views that it'll provide you. Those are obviously precipitation storms. This is the other satellite. The first satellite, the US, is kind of up and to the side. This, it's kind of down to the bottom. This one's off looking down. Anyway, I think it's pretty sweet. So that's just messing around with about $70 worth of hardware. The dish was about $100. It's about $170. You can talk to a satellite. So other attacks, we talked a little bit about water treatment plant. So I've audited water treatment plants, so I'm cheating a little bit because I know how it works, but I'm not sharing anything that isn't public information that you could find on Google like in 5 minutes. So almost everything on a water treatment system uses RS-485, which is a type of serial communication. Modbus, very widely used. Has anybody used or dealt with Modbus before? Nice, couple of you. Great. So widely used, very open standard, right? It's basically Ethernet. Then I did a little Googling and found out that the most widely used system, wireless communication systems in water that are marketed to water treatment systems for cities runs in these frequencies. Again, that was a 30-second Google. And those are in bands called ISM bands, industrial, scientific, and medical, I believe is what that stands for. And they're what's called unlicensed. So you have, if you remember at the beginning, that big pile of image they show you as the FCC band plan. All of those have different things and different things you can do in them. Some of them you have to have a license, like a ham license to broadcast in, which is an amateur license. Some of them you have to have a professional license, which means you said, hey, FCC, we're going to do this specific thing. We want to buy these frequencies, and we're going to do this thing in this area. Only let us do that, and they'll after you pay them a bunch of money, they'll let you do that. And then, but ISM bands are open. Okay, so that's where these are. Both of these are in ISM bands. Old wireless phones, house phones, run 900 megahertz. 433, some of your TPMS sensors run at 433, some of them run different frequencies, but they're all in open, unlicensed bands because then you don't have to get approved from the FCC. You just have to limit your broadcast strength to whatever it is. So I know they're running on these frequencies or thereabouts. I know they're using Modbus, which I can easily get libraries to decode that. But then you're like, well, then you still have to get the signal, right? So this is that little road there. I mentioned that I like to ride a bike a lot. So that little road there is called Murdoch Canals. Have you been on Murdoch Canal before? Yes. It's just this awesome path that runs through Orem and all the way to wherever, north, far. Anyway, so on Saturday, I was on a bike ride, and I'm like, man, I need a photo of one of these things so I can show the audience, right? So this is just a Google Maps image of this thing. So I didn't actually remember this was there, but I'm on my bike ride, and I'm looking around, I'm like, oh, there we go. So that's me from the path taking a photo of, in that building is a high concentration of chlorine gas in some sort of containers, right? Safety, they're all very safe. No one in this room has even heard of a leak other than it pools, so that's good, right? It's all very safe. And it's kind of hard to see, but in that break in the trees in the top there is a little mast. And on that mast is a Yagi antenna. So I'm not saying you could like capture data there, but you might be able to capture data there. We basically know what the frequencies those things are going to be broadcasting on, and you can kind of look at the Yagi. Once you get an eye for it a little bit, you can say, that's probably on this frequency or thereabouts. You'd have to get yourself in a position that's a directional antenna, right? So you'd want to get on the other side of it somewhere where it's probably where it's aiming. These are all over. Like there's one right up Rock Canyon. You go on a hike for about 30 seconds. There's a chlorine building up there with one of those Yagis that's about maybe 10 feet off the ground. You wouldn't have to walk too far away, point another Yagi at that thing, and figure out what it's talking about, right? I'm not going to say whether they control things, using that wireless communication, but they may control things using that communication. They may only report data using that communication. But that would be super interesting to control, and in the wrong hands, could be a problem, right? Like, it seems like we're most worried about our critical infrastructure at the moment, and water is about as critical as it gets, right? Water, power, gas. So it's a little bit more overt than like, how do you look at transmissions from the power grid? They probably use, I assume they use physical cabling for all those systems, but these remote locations, they have to use RF. So it's worth exploring. This kind of stuff's everywhere in RF. This is one example, but it's used so widely and probably protected so thinly that it's just encoding, right? Most of the stuff is just encoded. And encoding is not encryption. We all know that. So anyway, I would say go explore, spend $40, grab a dongle, grab some antennas, go just check stuff out. It's basically free. Any computer you have is going to have some software that you can run on it. Find stuff that might be interesting. Find something that has an antenna or an FCC ID. Hey, this is going to be broadcasting RF. Can I listen to it? Can I then replay those messages? Can I decode those messages? Can I then forge messages to make that thing do what I want it to do? A great next step is Michael Osman, he's kind of a guy in the SDR area, but he has a pretty good how-to on how to use GNU Radio. GNU Radio allows you to take messages, isolate that signal, and then you can take that, decode it, or have libraries that already decode it, forge messages, do all kinds of things like that. But dig in, check it out, look around. There's antennas everywhere, and I think they're all pretty interesting. Thanks for coming today. I appreciate it.